speed changes the rules of flight. Aircraft, rockets, and missiles operate under different aerodynamic regimes, depending on how fast they travel through the atmosphere. Once velocity exceeds Mach-5, 5 times the speed of sound, a vehicle enters the hypersonic regime. At that point, the air itself becomes dangerous. The Common Hypersonic Glide Body represents a new category of weapon designed to travel through this extreme environment while remaining maneuverable. Traditional ballistic missiles follow predictable trajectories. A rocket launches the payload into space, gravity pulls it back toward Earth, and the warhead descends along a largely fixed path. Because that path is predictable, missile defense systems can calculate intercept points. Hypersonic glide vehicles behave differently. Instead of falling directly back through the atmosphere, the vehicle re-enters and begins gliding at hypersonic speed. During this glide phase, it can maneuver laterally and change its trajectory. That maneuverability complicates interception. Defensive systems cannot rely on a predictable ballistic arc. The vehicle can alter direction while traveling at thousands of miles per hour. But maneuverability introduces its own constraints. Hypersonic flight generates extreme heat. As the vehicle compresses air in front of it, temperatures can exceed thousands of degrees. This is not caused by friction alone. Much of the heating comes from the compression of air molecules as the vehicle forces them aside. Engineers must design thermal protection systems capable of surviving these temperatures. Heat-resistant materials and specialized coatings protect the vehicle structure from melting or structural failure. Without these protections, a hypersonic vehicle would burn apart during flight. Another challenge appears in the form of plasma. At hypersonic speeds, the intense heating of air can ionize surrounding gases, forming a plasma sheath around the vehicle. Plasma is electrically charged gas, and it can interfere with radio signals. That interference creates a communications problem. Guidance systems must operate even when radio signals are partially blocked by plasma surrounding the vehicle. Engineers must design navigation systems capable of functioning under those conditions. Then there is control. Hypersonic vehicles travel so quickly that small control inputs can produce large changes in trajectory. Aerodynamic forces become extremely sensitive to surface geometry and angle of attack. Maintaining stability while maneuvering requires precise flight control systems. Even minor instability could lead to loss of control at extreme speed. The glide body itself is usually launched by a rocket booster. The booster accelerates the vehicle to hypersonic speed and carries it to high altitude. Once released, the glide body separates and begins its atmospheric glide toward the target. From that moment, the vehicle operates without continuous propulsion. Instead, it trades altitude for distance while maintaining enormous velocity. This glide profile allows the weapon to travel long distances while staying within the atmosphere, where maneuvering is possible. But this also exposes the vehicle to continuous heating and aerodynamic stress. Material science becomes as important as propulsion. Thermal shielding must survive repeated heating cycles. Structural components must resist extreme loads generated by high-speed maneuvering. Even guidance electronics must be hardened against vibration and heat. Despite these challenges, hypersonic glide vehicles represent a significant shift in strategic weapon design. Their speed compresses response time, their maneuverability complicates interception, and their atmospheric flight path blurs the line between ballistic missiles and aircraft. Yet the underlying physics remain unforgiving. Heat increases with speed. Control becomes harder as aerodynamic forces grow stronger, and materials must survive conditions that push the limits of engineering. Hypersonic weapons promise speed and unpredictability. But achieving that performance requires navigating one of the most hostile environments any aircraft can encounter. At Mach 5 and beyond, the air itself becomes the battlefield.